Welcome to the Deep Dive, where we cut through the noise and get straight to the most important insights from the latest research. Today, we're diving into the fascinating world of AI agents, specifically focusing on a significant breakthrough known as WebWatcher.
That's right.
AI has already achieved these almost superhuman cognitive abilities, as researchers put it, when it comes to complex information-seeking problems.
Things like planning multi-step tasks, searching the web effectively, reading documents.
Even refining answers through iterative reasoning. It's pretty advanced stuff.
It is. But despite those impressive strides, most of these advanced AI agents, they've been primarily text-centric.
Right. They've largely overlooked the huge amount of visual information out there in the real world.
Think about scientific diagrams, complex graphics you see online, or even just trying to understand a visually busy web page.
Yeah, integrating both vision and language for that kind of multimodal reasoning has been incredibly challenging for AI.
It really has. It demands, well, stronger abilities in perception, certainly, but also in logic, in understanding real-world knowledge.
And maybe especially in sophisticated tool use, right? Knowing how to find and use information.
Definitely.
And that seems to be the gap WebWatcher is designed to bridge.
Exactly. It's this groundbreaking development from Tanguy Lab at Alibaba Group. They present it as a multimodal agent for deep research.
And what makes it compelling, from what I gather, is its enhanced visual language reasoning capabilities.
That's the core idea.
So our deep dive today is going to explore how WebWatcher tackles these limitations, how it was trained.
The specific tools it uses, which are quite interesting.
And its, well, pretty remarkable performance on some brand new, challenging benchmarks.
So the fundamental challenge WebWatcher aims to solve isn't just about seeing, it's about reasoning about what it sees.
Okay.
And that needs strong abilities across both text and visual information, plus, as we mentioned, the effective use of various external tools.
Combining perception with the deeper understanding.
Precisely.
So how did they approach building this visual language world for WebWatcher? It sounds like the data must be key.
It absolutely starts there. They developed a really innovative pipeline specifically to generate high-quality training data.
Okay.
And this data is crafted for in-depth multi-step reasoning and strategic planning, not just simple lookups.
And where does this data come from? Is it synthetic?
No, and that's clever. They source it by essentially harvesting real-world knowledge. They use random walks over diverse web sources. Think of it like an automated process exploring interconnected information online.
Following leads, almost.
Kind of, yeah. And this lets them build these high-difficulty question-answering examples.
Examples that involve what? Multi-hop reasoning?
Exactly. Unpredictable multi-hop reasoning chains. Very similar to the kind of complex web research task you see in benchmarks like BrowseComp.
And they make it even harder, I read.
They do. They intentionally mask or obscure key entities in the question.
So the model can't just find the name. It has to infer relationships from the context.
Right. It forces inference rather than simple retrieval.
And for a multimodal agent, how do they bring the visual in?
That's their QA to VQA pipeline. It's pretty neat. It takes those complex text-based questions and answers and converts them into multimodal visual question-answering items.
Using real images.
Yes,
Yeah.
crucially, using authentic web images. So you get the visual richness, the noise, the complexity of real web visuals paired with that textual reasoning difficulty.
That sounds much more realistic than just clean, curated image data sets.
It is. And they have a rigorous multi-stage filtering process, they call it selector and examiner, just to ensure the quality and clarity of this massive data set.
Makes sense. You need good data to get good results.
Absolutely. And to really test these capabilities, the researchers didn't just rely on existing benchmarks.
So they made a new one.
They did. They introduced BrowseComp-VL. Think of it as BrowseComp, which is already tough,
Right.
but extended squarely into the visual domain.
So even more complex queries.
Yeah, the queries are long, BrowseComp-style, often entity-obfuscated, like in their training data. It demands cross-modal inference reasoning across text and images, plus thorough information seeking and high-level planning.
Wow. And is it structured in any way?
It is. It's organized into 5 major domains, and it has 2 distinct difficulty levels.
Okay, what's the difference?
Level 1 requires that multi-hop reasoning, connecting different pieces of info.
But the entities are still explicit.
Right. So it's more about integrating information from different sources, visual or textual.
I love it too.
Level 2 is where it gets significantly harder. The questions have intentionally obscured or fuzzified entities and attributes,
Then
meaning the agent can't just look things up directly. It has to plan, it has to compare different pieces of information it finds, synthesize knowledge.
to actually arrive at an answer.
Yeah,
It's pushing way beyond simple retrieval.
definitely. It's a real test of reasoning.
Now, for an agent to do all this searching and reasoning, it needs tools. What's in
Yeah.
WebWatcher's toolkit?
It's got a pretty comprehensive set. There's web image search, naturally, web text search,
Standard stuff.
the ability to actually visit web pages, which is important for digging deeper,
Okay.
a code interpreter, presumably for calculations or data manipulation,
Interesting.
and an internal OCR capability.
Optical character recognition, so it can read text directly from images it finds.
That's right. So it can pull text out of diagrams, charts, photos, whatever it encounters.
That combination seems powerful. The integration of these different tools must be key.
It is. And teaching WebWatcher how to use them effectively and how to reason involved another automated pipeline
For training.
for generating training data, specifically reasoning trajectories. These are sequences of think, act, observe cycles.
Like decide what to do it, see what happens, then decide the next step.
Pretty much, yeah. Mimicking a human problem-solving process. And importantly, these trajectories aren't just theoretical. They're grounded in actual tool use behavior.
So they reflect the kind of procedural decision-making needed for these complex tasks.
Correct. And again, quality control is vital here.
How did they filter these trajectories?
A three-stage process. First, does the final answer in the trajectory actually match the ground truth?
Makes sense.
Second, is there step-by-step consistency? Does each step logically follow from the previous one without weird jumps?
Okay.
And third, a minimum tool usage requirement, at least 3 tool calls per trajectory.
To ensure it's actually engaging in multi-step reasoning, not just a single lookup.
Right. And then they train the agent. It starts with what they call a cold start phase.
Using supervised fine-tuning, or SFT.
Yes, SFT on these high-quality trajectories. This basically teaches the agent the foundational skills of tool-augmented reasoning.
Building the base capability.
Exactly. And following that crucial SFT cold start, they then apply reinforcement learning, specifically a method called GRPO,
And the goal of the RL phase.
to further optimize WebWatcher's tool use and its decision-making strategy, to make it more efficient, more adaptive in how it solves problems.
Refining those learned behaviors for complex, dynamic situations.
Making it smarter about how and when to use its tools.
So after all this complex training and data generation, what did WebWatcher actually achieve? How did it perform?
Well, the results are quite impressive, frankly. WebWatcher significantly outperforms proprietary baseline models, common ARG workflows you see a lot,
Right. Retrieval augmented generation.
and other open source agents across 4 really challenging visual QA benchmarks.
Which ones were they?
Humanities Last Exam HLE, that new BrowseComp-VL we discussed, Live VQA, and MM-Search.
And it also did well on simple VQA.
Showed competitive performance there too, yes. But the key is the significant outperformance on the harder ones. It wasn't just a small edge.
Let's maybe look at humanities last exam specifically. That sounds like a tough one.
It's incredibly demanding, and typically models that just try direct inference without complex reasoning or tools score very low, usually below 10%.
Even with RAG.
Even RAG approaches only show moderate improvements there. But WebWatcher, the 32 billion parameter version, achieved a new state-of-the-art result.
What was the score?
An average of 13.6% pass rate on the first attempt, pass at 1, which substantially beats strong baselines, including some advanced models based on GBC 4.0.
Wow, okay. Any specific areas where it really shone?
Yes, the paper highlights particularly significant gains in challenging domains like biology and physics.
Areas where integrating complex diagrams or visual data with text is crucial.
Absolutely.
And what about performance across the other benchmarks? You mentioned Live VQA, MM-Search.
Strong scores there too. 58.7% on Live VQA, 55.3% on MM-Search, and 27.0% on BrowseComp-VL.
That BrowseComp-VL score, 27%, might sound low, but you said most baselines struggle to get past 20%.
That's right. It really underscores the difficulty of that benchmark and highlights the benefit of WebWatcher's dynamic tool use loop. It consistently delivered more stable and superior results, especially on demanding real-world visual search tasks like MM-Search.
And you mentioned its tool use was adaptive. It didn't just use the same strategy everywhere.
No, not at all. The paper has a great figure illustrating this. It shows how WebWatcher intelligently adapts its tool usage based on what the benchmark demands.
Can you give an example?
Sure. For Humanities Last Exam, which has incredibly diverse tasks, no single tool dominates. Web text search, web image search, and the code interpreter each account for about a quarter of all tool calls.
So it's flexing all its different muscles there.
Right. But then you look at BrowseComp-VL, which is heavily focused on finding and integrating web information, and suddenly 62% of its interactions are using web text search, much less reliance on images or code.
It focuses on the best tool for that specific job.
Precisely.
Right.
And then for the more visually driven benchmarks, live VQA, simple VQA, search, web image search usage jumps up, accounting for around 1/3 or more of all calls.
So the distribution of tool use really tracks the skills needed for each specific benchmark.
It does. It showcases the model's ability to, flexibly choose the right chain of tools for the problem at hand.
That adaptability seems crucial. You also mentioned the cold start SFT phase was important.
Indispensable. According to the researchers, they actually tested what happens without it.
What did they find?
If they just used the base instruction-tuned model and tried to go straight to reinforcement learning, the agent's performance stayed near zero.
Zero. Why?
Mostly due to errors in just making the tool calls correctly.
Yeah.
It hadn't learned that foundational layer of how to interact with the tools reliably.
Okay. So the SFT phase provides that essential foundation.
Exactly. That cold start SFT lifted the initial scores significantly to, for instance, 12% on HLE, 30% on BrowseComp-VL, and 45% on live VQA before the RL refinement even started.
So it really highlights how critical that initial structured fine-tuning is.
Very much so. You need that solid base.
Okay, one last performance aspect, this PASIC-K analysis. What does that tell us?
PASIC-K basically measures the success rate as you allow the agent more attempts, or K attempts, at solving a problem.
So if it doesn't get right the first time, try again a few times.
Right. And on humanities' last exam, we saw the pass at 1 was 13.6%. Already impressive. But if you allow just 3 diverse attempts, so K equals 3, the score jumps to 20.3%.
That's a pretty big jump for only 2 extra tries.
It shows a substantial benefit from getting just a handful of complementary perspectives or approaches from the model.
And does it keep improving with more attempts?
It does. It reaches 35.7% at 16 attempts and 41.9% at 32 attempts.
Wow, so 32 trials almost quadruples the success rate compared to just 1.
Yeah. And what's interesting is the shape of the curve as Kook increases. It's smooth with no sudden big jumps.
What does that imply?
It suggests their sampling strategy for generating these multiple attempts is working well. It's generating genuinely different, mutually informative trajectories.
Rather than just slight redundant variations of the same failed approach.
Exactly. Each new attempt seems to bring potentially new insights, which is really key for tackling these complex multi-step problems reliably.
So if we were to wrap this up, WebWatcher seems like a really significant step forward.
I think so. It introduces this unified framework that successfully combines that complex vision-language reasoning
With sophisticated multi-tool interaction.
Right. It definitely establishes a strong foundation for future multimodal agents focused on deep research. It shows what's becoming possible when AI can not only read, but truly see and interact with information more like we do.
It really pushes the boundaries.
It does. And maybe the final thought for you, the listener, is to consider this. How does an AI like WebWatcher, one that can autonomously, flexibly, and deeply reason across both text and visual information, how does that change our picture of what AI can ultimately achieve?
Especially in solving those really tricky, real-world information-seeking problems that combine everything.
Problems that were, until recently, probably well beyond AI's grasp. It opens up a lot of new possibilities.